Hello students and welcome to the lecture. So students, as we know that we are covering the Newton's laws of motion, right? So far we have completed the 3 part. Now we are going to start with the part 4. Okay. It is the Newton's laws of motion part 4 that we are going to start. I hope that you have revised the previous lectures in the well enough manner. Before you have come for this lecture, as many times I have reminded you, it's for your own benefit. Okay. So basically in this lecture, what we are going to see, we are going to talk about the some terms related to machine. Like in the previous lecture, if you remember, we have taken the introduction of the machine, right? Now we are going to talk about the some terms that are related to machine. Then we will talk about levers, kinds of levers, principle of conservation of linear momentum, and at last we will see the summary of all of them. Okay, so like you can say some terms related to machine, levers, kinds of lever, principle of conservation of linear momentum, and at last the summary of all these things. Okay, but before starting, as usual, we have our small disclaimer over here that we are required to understand first before we proceed further. So the disclaimer is like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this tag and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's begin with the topic. First is mechanical advantage. So what do we mean by this? The ratio of load to the effort is called the mechanical advantage of the machine. Like if you remember in the previous lecture when we were discussing about the machine, there we had come to know that basically in machine, we have to give some input, machine process it, we receive the output that we're desiring for, right? And in terms of the idle machines, basically the ratio of input and output is equal. Suppose if you supply 10 as an input, machine will process it and you will receive 10 as output. Okay, but generally it is not happen because no machine is an idle machine. All right, so generally what happened, the ratio of input and output, the input is always higher in comparison with the output. Okay, like suppose if you put 10 as an input, you may receive 8 as an output. Okay, so that is what written down here as a mechanical advantage. Like mechanical advantage is the ratio of the load to the effort. Okay, is called the mechanical advantage of the machine. Like how much load you have put in how much effort and how much you have got the efficiency. It having no unit, mechanical advantage is equal to load by effort. Thereafter, the another thing that is related with this is the velocity ratio. The ratio of the velocity of the effort to the velocity of the load is actually called the velocity ratio of the machine. Okay, and the velocity ratio is velocity of effort by velocity of load. Okay, now if dl and de are the distance moved in time t by the load and the effort respectively. Okay, this is the distance of load, this is the distance of efforts, and this is the time taken by them while moving. Okay, then velocity of the load will be dl by t ratio de by t. Okay, like distance of load by time, distance of effort by time. And the velocity ratio will be velocity of effort by velocity of load. It means de by t by dl by t is equal to de dl or de by dl. Got it? So remember this thing. Now some terms that are related to machine. Thus, velocity ratio is also defined as the ratio of displacement of effort to the displacement of load. Okay? It also having no unit. So you can say basically while calculating the velocity ratio, we could take the ratio of the displacement of effort to the displacement of load. Also, we could take the ratio of the displacement distance of effort to the distance of load. Okay, it is also not have any unit. After this, now we have the efficiency. Okay, so efficiency of a machine is actually the ratio of the useful work done by machine to the work put into the machine by the effort. Okay, like you can say what useful work the machine has provided you after putting the work input into the machine. For example, you can say, suppose there is any machine, your input is 10, the machine is processing it, give you output 8. Okay, useful output 8. Another machine is also there, you give the same input of 10 into that machine, the output is only 6. So now you can say there is a mismatch or disbalance between 8 and 6. Between 8 and 6. Got it? So if I ask you, like which machine is giving you the best useful work? By comparing 8 to 6 or 6 to 8, you can say the machine that is giving us the useful output of 8 is more good in comparison with the machine which is giving us the output 6. Okay, so which means the first machine giving out output 8 is more efficient than the machine which is giving output 6. That is the efficiency. In other words, it is the ratio of the work output to the work input. Like how much work output you got after putting the work input. So if you go by the example that we have just taken, first machine having the ratio of 10:8. Another machine is having the ratio of 10:6. Just look at the ratio. You will find out the input 10 was same. In the first machine, you gave the same input. In the second machine, you gave the same input. Output is different. The first machine give you output 8 while the another machine give you output 6. So efficiency of the first machine which is giving you the output 8 is more in comparison with the machine which is giving you the output 6. Okay. So now I hope you have got the efficiency. Efficiency is usually expressed as a percentage, so we many write it. Efficiency is equal to work output by work input into 100. For example, if the work output is 8, work input is 10 into 100, you will get what? You will get 8%. Similarly, if the work output is 6, work input is 10 and you are getting 6%. So the efficiency of the first machine is 8% while the efficiency of another machine is 6%. It is also not having any unit. The efficiency of an idle machine is 100%. Like in the beginning of this lecture, I had told you. In the previous lecture also we had discussed that basically in machine all the things that start with the input and output. Okay, how much input you are giving, how much output you are generating. It is the simple calculation to calculate out the machine mechanical advantage, machine velocity ratio, as well as the machine's efficiency. Okay, so in the case of the realistic machine, I'm not talking about the idle machine. In the case of the realistic machine, the ratio between the output and the input will be unequal. Input always higher in comparison with the output when we talk about the realistic terms. In the idle machine condition or in the idle situation, both are 100%. Okay, like work output is 100, work input is 100, into 100 you will get 100%. Okay, but in the realistic scenario, this is not that much possible. No machine can having the efficiency greater than 100, not even the idle machine. Because if you say this, the efficiency is more than 100, it simply means that your output is much more higher than your input. Okay, like if we take our examples. So in our example, 8 was the output, 10 was the input, 8% was the efficiency. Ideal machine, 100 is the output, 100 is the input, 100% is the efficiency. So there you can say there are the three cases that we could draw from this scenario. First case, output is lower to the input. Second case, output equal to the input. Third case, output is greater than the input. In all these three scenarios, first scenario is possible and it is mostly applicable, that the output is low in comparison with the input. Second scenario is for the ideal machines, where the output is equal to the input. But the third scenario, where the input is lesser than the output, or you can say the outer is more than the input. Suppose here the input is 100, output is 110. So how much you will get? You will get almost 11%. Okay, 11% will be the efficiency, that is okay. But scenario is that your output is higher to the input. That is not possible. Okay. In practices, however, no machine is idle. Why? We know no machine is idle machine. No machine could have the same output as the input. But do we know the reason why it is happening? We know the consequence, but do we know the reason? That is what we have to figure it out. So first, if we talk about the reason, the moving parts in it are not perfectly smooth. Even if you look at these, now you will say that these are smooth and these are shining and all. Okay, yes, these are. But the question is perfectly. These are not perfectly smooth. Thereafter, the string in it is not perfectly elastic. Okay, like many times if you open any machine, you will find out that there are the strings as a mechanical part of that machine. The strings must be elastic so that they could easily deform and easily regain their original shape. Okay, but these are also not perfectly elastic, although these are elastic but not perfectly elastic. Then its different parts are not perfectly rigid. If you look at this picture, you will see that it is having some blanks in it, which makes its surface as a rigid surface. Okay, it is rigid but not perfectly rigid. Here we are not talking about the characteristic like smooth, elastic, rigid. We're talking about the perfection in them. We're talking about the perfectility in this comparison. Its moving part are not weightless. Okay, like if there is some machine which having some moving parts, these moving parts are not weightless. So if you give 10 as an input, okay, while processing, some part of this input will be utilized to move the part. Why? Because the parts having their own weights, they require their own efforts and own energy to move. Okay, so some of your input will be consumed there. So the relationship between efficiency, mechanical advantage and the velocity ratio is equal to efficiency n is equal to ma by vr, or ma n is equal to vr into n. Okay, that is the relationship between these three: efficiency, mechanical advantage, velocity ratio. Okay, for an ideal machine which is free from friction, the efficiency is equal to 1 or 100%. Here we say free from friction, which means no resistive force is there. All the parts are doing well. They are perfect. Even they are moving perfect. Okay. So if you give 10 input, then your output will be 10. Why? Because no part of your input is going to face this friction. Every part is moving without having any influence of friction. Okay. So that's why the efficiency is equal to the 1 or 100%. So the mechanical advantage is numerically equal to the velocity ratio in the cases of idle machines. In actual practice, if we talk about the realistic scenarios, the mechanical advantage of a machine is always less than its velocity ratio. Okay, MA is always less than the VR, or efficiency will always be less than 1%, therefore N is less than the 1 or the 100%. This is the actual practice or real scenario. This is for the idle machine cases only. Levers are the simplest kind of machines used in our daily life. If we talk about, a lever is also a rigid, straight or bent bar which is capable of turning about fixed axis. Okay. Now, if we talk about the levers, that is what we are going to say. So first we have the fulcrum. Okay. What is a fulcrum? So it is the axis about which the lever turns, passes through a point of the lever which is called the fulcrum. Like if you look at this, suppose if this is the lever, so you can say this is the fulcrum. Okay. It is the point from where the lever turns. Okay. The principle of lever, MA of a lever, which you can see in figure AB, is a lever with the fulcrum at F. An effort E applied at a point A of the lever overcomes a lead L at the point B. The distance AF of point A at which effort is applied from the fulcrum F is called the effort arm, and the distance BF of point B at which the load acts from the fulcrum F is called the load arm. Okay, so effort arm is this one. Okay, let me clean it first. Effort arm is this one, and the load arm is this one. Okay. An idle lever works on the principle of moments, neglecting the friction and assuming that the lever is weightless. Okay. So when the lever is in equilibrium, by the principle of moments, the clockwise moment of the load about the fulcrum is equal to the anti-clockwise moment of the effort about the fulcrum. Load into load arm is equal to effort into effort arm, or L into BF is equal to E into AF. Okay. Why we take BF? Because BF was the distance between the, or you can say this distance was basically the load arm. Why we take AF? Because this distance was the effort arm. So L by E, load by efforts, equal to AF by BF, but L by E is equal to MA, or mechanical advantage, or mechanical advantage equals to effort arm AF by load arm BF. This relation is known as the law of levers. Now the kind of levers. So depending upon the relative positions of the efforts, load and fulcrum, we have three types of levers here. First lever, it's a class 1 levers. In this type of lever, the fulcrum F is in the between the effort E and load L, as shown in figure example. Assume a pair of scissors, crowbar, handle of water pump, claw hammer or pair of pliers, and the beam of the common balance, a spade used for learning the soil, the bottle opener. These all are the example of class 1 levers. For class 1 levers, the mechanical advantage, the velocity ratio, could have any value greater than 1, equal to 1, or less than 1. Okay, which means in all the scenarios it is possible. When the effort arm is longer than the load arm, mechanical advantage and velocity ratio are greater than 1. If the effort arm and the load arm, they both are equal, no one is greater than anyone, the mechanical advantage and the velocity ratio equal to 1, while the effort arm shorter than the load arm and the mechanical advantage and velocity are less than 1, then it will happen. So you can say in the all the scenarios, if we talk about, so when the mechanical advantage and the velocity ratio will be greater than 1, the effort arm will always be longer than the load arm. In case where they both are equal to 1, effort arm and the load arm both are of the same size or the same length. In the case where it will be less than 1, mechanical advantage and velocity ratio, if they both are less than 1, mechanical advantage and velocity ratio, they both will be equal, are short. Or you can say effort arm is shorter than the load arm, then it will be having the value less than 1. A lever of mechanical advantage greater than 1 is used as force multiplier, while a lever of mechanical advantage less than 1 is used to obtain the gain in speed. Second class that we have is the class 2 levers. In this type of lever, the load L is in between the effort E and the fulcrum F, as shown in the figure. Okay. The effort arm is thus always longer than the load arm. Example, a nutcracker, wheelbarrow, a lemon crusher, a paper cutter, a mango cutter, an oar used for rowing a boat, a bar used to lift a load are examples of class 2 levers. The mechanical advantage and velocity ratio of class 2 levers are always more than 1. Okay. Down we have the class 3 levers. In this type of lever, the effort E is in between the fulcrum F and the load, as shown in the figure. Here you can say. In this lever, the effort arm is always smaller than the load arm. Examples are sugar tongs, the forearm used for lifting a load or action of the bicep muscle, fire tongs, food treadle, knife, etc. These all are the examples of class 3 levers. Mechanical advantage and velocity ratio of class 3 levers are always less than 1. Now we have principle of conservation of linear momentum. So if we go by this principle, we could say, according to this principle, in an isolated system, okay, what is the isolated system? Isolated system is a system of bodies where the influence of any external force is negligible, or that's why this system is free from any influence of any external forces. The vector sum of the linear momenta of all the bodies of system conserved and not affected due to their mutual action and reaction. Therefore, when two or more bodies act upon one another, their total linear momentum remains constant or conserved provided no external force are acting. If you look at this picture, before collision they have, during collision, after collision. So you can say their linear momentum remains constant. Okay, but there is a condition when no external force acting or applied. Once the external force is acting or applied, the condition will not be there. The law of conservation of linear momentum means that whenever one body gains momentum, whenever the one body gains momentum, then some other body must lose an equal amount of momentum. If m1, m2 are the masses of colliding bodies and u1 and u2 are the velocities of the bodies respectively before the collision, and v1 and v2 are the velocities of body after the collision, then by the law of conservation of linear momentum, we could say m1 u1 plus m2 u2 is equal to m1 v1 plus m2 u2. Okay, that will remain same before and after the collision if no external force are acting. We have finished the topic. Now it's part for the summary discussion. We have talked about the key concept related to the machines and levers, like mechanical advantage we have talked, velocity ratio we have talked about, efficiency we have talked about, relationship between efficiency, MA and VR we have talked about, levers we have talked about, what is the class 1 levers we have talked, class 2 levers we have talked, class 3 levers we have talked. After this, we have talked about the law of conservation of linear momentum, and also we have talked about the principle of moments for levers, that in the equilibrium, clockwise moment of the load equals to the anti-clockwise moment of the effort, leading to m is equal to effort arm by load arm. So with this, we have finished this lecture. It is requested to all of you, Kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.